Lecture 5, Predicting Quality in Healthcare, Part 3. So after building our model, logistic regression model, you know that the outcome of a logistic regression model is a probability, a number between 0 to 1. But we need to make a class prediction, right? I mean, in order to be able to compare the result of our model and the actual data set, the actual outcome, we need to see if the quality of healthcare received by this patient is poor or good, right? So in order to obtain these two outcomes by having a probability obtained by the logistic regression, we can consider a threshold value at t, right? So by having that threshold value, then we can say, okay, if the probability obtained by the logistic regression model is greater than or equal to t, then consider that as poor quality. That means y equals 1. Okay, and if that probability is less than t, then consider that as good quality. That means the y equals 0. So yeah, by having a threshold value t here, we can segment the obtained probabilities to be in the two class of 1 or 0, right? So, but here the question is, what should be the value of that threshold t? In selecting a right value for the threshold t, we can see which error is better for us. So let's first consider the most popular approach. The most popular approach is assuming threshold t as 0.5, and the rationale behind this selection is considering the class based on the higher probability. Okay, so it makes sense, right? But let's have a discussion here. For example, in our case, if we consider the t pretty large number, not 0.5, for example, let's say 0.8, okay, then here predicting the poor quality will be happen rarely, right? So that means we will have more errors where we say good care, but the actual outcome is poor care, right? So in this case, we will detect the patients as poor care when they are receiving actually very, very poor care. I mean, they are the worst case, right? Worst cases. And if we consider a small value for t smaller than 0.5, let's say, for example, 0.2, 0.3, then the predicted good care will rarely happen, right? So that means more errors when we say poor care, but the actual outcome is good care. Okay, so in this case, we can say we can detect almost all patients who might receiving poor care. Okay, so in any situation like this, we should see which error is better for us. In the second scenario here, I mean here when we assume a small value for t, we have errors in obtaining good cares as poor cares, right? But the good side here is detecting almost all patients who are receiving poor care. But in this first one, our error is about predicting good care for the ones who actually received poor care, right? So that means here we are not going to detect almost all patients who are receiving poor care, just the ones are the worst case. We are predicting those ones. So if detecting almost all the most patients who are receiving poor care is so important to us, then we should go with a small value for t in this case, in our case. But if not, then we can go with a larger t. So yeah, it depends to the context of the case and analyzing which error is better, or which error is so important for our case. Then based on that, we can see what value of t, the threshold, could be better for our model. Okay. So by any threshold value of t, we can build a confusion matrix like this in order to compare the actual outcomes and the predicted outcomes. So as you see here in the first row, we have the actually good care, right? And in the first column, we have the predicted good care. So this cell would be considered the true negatives, right? True negatives. And if we predict poor care for the actually good cares, then we consider this as false positive, FP. And for the second row, we have actually poor care, y equals 1. So, and but we predict good care, so it will be false negatives. Okay, and if we predict poor care for the actually poor care, then we consider this as true positive. Okay, true positives, TP. So, and a different value of T will change the outcomes in this confusion matrix. Okay, so now we can define two measures here. The first one is sensitivity, and the second one is specificity. Okay, so in the sensitivity, we consider. Let me show here. Yeah, we consider this row, and we divide this outcome over the sum of the two outcomes. Okay, so true positive over true positive plus false positive, right? So here we assume that we are focusing on the population of actually poor cares, and then we consider our prediction, and then true positive will be divided by true positive plus false positive among the actually poor cares. And for the specificity, we consider the first row, and same as the previous case, we divide the true negatives over the sum of the two categories, I mean true negatives and false positives. Okay. So let's have some examples here. Let's assume that the threshold value here is 0.5, okay, 0.5. So this will be the outcome, I mean the performance of the model. So here we assume that we have 74 good cares, actual, I mean in actual y equals 0, so that means good cares. So, and we have predicted 70 items, I mean 70 patients out of 74 as good care, right? So then just we have error just for 4 patients, right? So 70 divided by 70 plus 4, I mean 74, which will be 0.95. So that means among the good cares, we have predicted our accuracy is 95%. We have detected 95% of good cares as good care, right? So in terms of the good cares, it's good. Now let's go for the bad cares, I mean the poor cares. So here, as you see here, the sum of these two numbers, 15 plus 10 is 25. That means in our data set, we have 25 patients that received poor cares. But here, we have detected just 10 of them. I mean, actually poor and predicted poor is just 10. So 10 patients out of 25 predicted correctly, and 15 patients of those 25 patients we predicted as good care, but actually they have received poor care, right? So here we have the sensitivity. So as you see here, 10 over 25 becomes 0.4. So that means here our performance on detecting the low care, the poor care, is not good. We are just predicting the 40% of them, and 60% we have error. Okay, so now let's change the threshold value to be 0.7 and see what happens. So I'm not going to explain again the numbers here, so because you know what they are. Let's just focus on the values here. So by 0.7, the situation becomes worse actually. As you see here, the sensitivity drops from 0.4 to 0.32, right? So that means among 25 low level for low quality, we just predicted 8 of them, and for 17 of them we have error. But for the good cares, we have actually good performance here, and we are predicting 99% of them as correctly. Now, so as you see here, the higher T results in bad performance on detecting the low quality care, right? So now let's decrease the threshold value to be 0.2. Okay, so now we have better situation in terms of detecting the low level cares. So I see here, among 25, we predicted correctly 16 of them, right? So now we have 0.64. 64% we have accuracy in detecting the low level cares. But for specificity for detecting good cares, our performance is 0.73. So now this threshold actually in terms of in our example, this threshold is better than 0.5 and 0.7 because here we are detecting correctly 64% of low level cares, and we can actually refer them and intervene the medication to improve the performance. Okay. In order to analyze the impact of different values of threshold in the performance of our model and pick the right value for the threshold, we can use the receiver operator characteristic curve, or ROC curve. So in this curve, ROC, the horizontal axis is false positive rate. So it is 1 minus specificity. So that means a proportion of good care labeled as poor care. So that means actually we have good cares, but our model predicts them as poor care. Okay, so because of that, it's called false positive rate here. And in the true positive rate, this is actually the sensitivity of the model. So, we have actually poor care, and our model correctly predict them as poor care as well. Okay. So this curve is drawing based on different values of t. So each point, any point on this curve, refers to a specific value of t. Okay. For example, this area refers to the lower t. Okay. So that means if we consider a small value for the threshold, then we often predict y equals 1, right? And if we increase the threshold value, having higher t, then we will be in the in this area. In the left bottom side of the curve. That means we rarely predict y equals 1. Okay, so ideally we want to be somewhere here in the left top corner, because in that area we have higher true positive rate and lower false positive rate. For example, in this curve, maybe these numbers here could be a good choice for the value of threshold in the model. Okay. Okay, by having an ROC curve, we can do a trade-off between the cost of failing to detect positive and the cost of raising false alarms. And as I said, usually this area as close as to the left top corner is the best area to choose the threshold value. Okay. Okay, we will see later how can we generate ROC curve in R, and this is an example of ROC for our data set by assuming different values for threshold. We can add colors and labels to our ROC curve, and then this will help to easily obtain the right choice for the threshold. So in this example, as you see, the blue colors refer to lower threshold, right? And we have it here. So this part of curve is about lower threshold value. And the red color refers higher value for the threshold, and we have it there here. So this part of the ROC curve refers to the higher threshold value. So if we want to be as close as to the left top corner, the ideal area for the threshold value, then 0.2 here could be a good choice for the value of the threshold. Okay, so we will see how we obtain ROC curve in R in another recording. Okay, thank you.